Now we're going to look more closely at cardiac output and the things that can alter it. So cardiac output is the amount of blood that a single ventricle pumps into an artery in 1 minute. So you have two cardiac outputs. You have the right ventricle pumping into the pulmonary trunk, and you have the left ventricle pumping into the aorta. Ideally, these will be equal to each other. And later we'll talk about what happens if they're not equal to each other. But in a healthy person, these two ventricular cardiac outputs are equal. So let's think about what determines cardiac output. It's the amount of blood the ventricle pumps into an artery. Well, that should sound familiar to you. That is your stroke volume. And in 1 minute, that has to do with your heart rate. So we already know that stroke volume in an average healthy adult at rest is 70 milliliters. We also know that heart rate for an average healthy adult at rest is 75 beats per minute. So if your heart is beating 75 times in a minute, and each time it beats, it pumps 70 milliliters of blood into the artery, we want to know how much blood got pumped into that artery during that minute. It's very simple. Cardiac output is heart rate times stroke volume. You just multiply your heart rate by your stroke volume. So an average healthy adult at rest has cardiac output of 75 times 70. And that comes out to 5,250. This is milliliters per minute. Since this is metric, you can move the decimal. So instead of saying 5,250 milliliters per minute, we're going to move the decimal over and say 5.25 liters per minute. So standard cardiac output is 5.25 liters per minute. And remember, that is per ventricle. So going into the pulmonary trunk, you have 5.25 liters every minute. Also, going into the aorta is 5.25 liters per minute. So here are two things that determine cardiac output. Remember, we have the node and we have the muscle. Node is in charge of heart rate. It controls how fast your heart beats. And you have that cycle. We start at -60. The -60 causes the sodium gates to open, and sodium comes in. Sodium comes in and raises the voltage to -40. This stimulates the calcium gates to open. Calcium comes in, raises the voltage to 0. This stimulates potassium gates to open, and potassium goes out, and your voltage goes back down to -60. Then we have our muscle. It works because you have calcium from your sarcoplasmic reticulum plus calcium that enters through your calcium gates from outside the cell. So you get your total amount of calcium inside the myocardial cell. This binds troponin, which then moves tropomyosin, so that you can form cross bridges. More calcium means more cross bridges. The more cross bridges you have, the more force you have. And the harder the heart squeezes, the higher the stroke volume. So you control your stroke volume by controlling how much calcium enters. This one right here is how you alter your stroke volume. So that's the basics of cardiac output. You can change cardiac output by changing your heart rate or stroke volume or both. So now let's start exploring this. Things that are going to affect heart rate and stroke volume, which will then in turn affect cardiac output. Let's take a minute to talk about kids and athletes, because we've said that 75 is the standard heart rate for an average healthy adult at rest, but not everyone is an average healthy adult. So if we think about kids, kids are small. They're smaller than adults. That means their heart is also small. If their heart is small, then their stroke volume is going to be low because you can fit less blood in that ventricle. So a small heart has a lower stroke volume. In order to compensate for this lower stroke volume, you have to have a higher heart rate. Okay, think about if you're filling up a bucket. If we have a bucket and I tell you to put water in the bucket, if you're an adult, here's an adult, and you have to put water in the bucket, and I give you a big, 32-ounce mug. Like you go to the gas station, you get one of those big 32-ounce sodas, and that's what you use to fill the bucket. Let's say we have a kid, and I give the kid just a little 8-ounce. So let's say this is a 32-ounce, this is an 8-ounce. And the kid has to fill the bucket, but his cup he's using to pour water in is only 32 or is only 8 ounces. Well, the kid is going to have to do more trips, right? You can walk over to the sink, fill your 32-ounce cup, go dump it in the bucket. You can do that in a few times and you're going to have the bucket full. The kid is only carrying 8 ounces at a time. So the kid is going to have to make more trips to the sink and back to the bucket in order to get the bucket full. Now let's say that I give you 1 minute. So you have to have this bucket full in 1 minute. Well, you can walk nice and slow, take your time. The kid, however, is going to have to run back and forth really fast in order to get that bucket full in 1 minute. So kids have higher heart rates. For a child, a resting heart rate is in the hundreds. Then if we look at athletes, athletes are the opposite. We've talked about them before with their heart rates in the 40s. Athletes have a strong heart. If you remember last semester when we talked about oxygen use and going into fermentation, if you're out of shape and you try to run a marathon, you're not going to make it very far. If you train, you will be able to do it. And one of the things that changes when you train is that your heart and lungs get better at sending oxygen to your muscles. That's why you're able to run for a longer period of time. So athletes, because they train, they have a much stronger heart. The force is increased. Athletes have more force every time their heart beats. So because their heart is strong, it has more force. And because they have more force, they have a higher stroke volume. So if we threw an athlete in here with the bucket, here's an athlete, someone who regularly trains and runs marathons. We're going to give the athlete a great big, like a 52 ounce. You know, Casey's has those giant 52 ounce mugs. That's what we're giving the athlete. So he has an even easier time filling up that bucket than the adult or the child. So because athletes have such a high stroke volume, they don't need their heart to beat very fast. So an athlete's resting heart rate can be about 40 to 50. Okay, now let's look at chronotropic agents. So if we break this word down, chronotropic. Chron means time. Think of like chronology. It means putting things in order of time. So chronotropic agents are things that will alter your heart rate. Heart rate is about time. It's beats per minute. So chronotropic agents are going to alter heart rate. That means they are going to do it by acting on your node. The node, remember, is in charge of heart rate. So chronotropic agents are any outside force that's going to stimulate the node and tell it to go faster or slower. Let's go back and review what's going on in the node. You have your nodal cell, and you have that cycle. You start at -60, then you let sodium in. That takes you to -40. Which makes the calcium gates open. You let calcium in. This takes you to 0, which causes the potassium gates to open. Potassium goes out, and you're back to -60. We know that parasympathetic is going to have acetylcholine from the vagus nerve, and that will open potassium gates. So when you have parasympathetic, you have extra potassium out, which gives you then even more negative. You will hyperpolarize, which means that it takes longer for the sodium to get to -40. So parasympathetic is a negative chronotropic agent. Because it decreases your heart rate. Then we have sympathetic. So remember, sympathetic works because your cell has beta receptors. Norepinephrine binds to the beta receptor. That activates cAMP. C-amp then opens a calcium gate and lets extra calcium in. So when you have norepinephrine, you get extra calcium in. That means you go this part faster. You go from -40 to 0 faster. So with sympathetic, norepinephrine binds the beta receptor. You activate C-amp. This opens calcium gates so that you have extra calcium to go from -40 to 0 faster. So you have parasympathetic and sympathetic are your main ones here. So sympathetic is a positive chronotropic agent. Because it increases your heart rate. Okay, then we have other things that can come in and alter this. So if we look at some other chronotropic agents, we're going to have thyroid hormone. So take a minute and go back to chapter 17 and review thyroid hormone. Is it water soluble or lipid soluble? And what are the implications of that? What is it going to make the heart cell do? So thyroid hormone is lipid soluble. And we know that lipid soluble hormones stimulate cells to make protein. Now take a minute, look at your pre-class assignment. What are some examples of proteins on cells? What protein is the thyroid hormone going to make this nodal cell in the heart make? So beta receptors are proteins. Receptors on cells are proteins. So start putting 2 and 2 together. Thyroid hormone is lipid soluble, so it's going to stimulate the cell to make protein. Beta receptor is protein. Thyroid hormone causes the nodes of your heart to have more beta receptors. So they're upregulating. Remember in chapter 17, cells can change their number of receptors, upregulate or downregulate. So thyroid hormone makes your heart upregulate to norepinephrine. So when you have thyroid hormone, you're going to have more beta receptors. You get all these extra beta receptors here. If you have more beta receptors, you're going to bind more norepinephrine. And for each norepinephrine you bind, you're going to get a C-amp. And that C-amp is going to go open more calcium gates. So the result of that is there's going to be more calcium coming into the cell. So more beta receptors means you will bind more norepinephrine, which means you will have more C-amp, which means you will open more calcium gates, and you will let even more calcium in. And that will make you go from -40 to 0 even faster. Another one is caffeine. You may have noticed if you drink a lot of coffee, your heart kind of racing, or like those energy drinks. There have even been people have heart attacks from drinking those energy drinks because they make your heart race so fast. So caffeine speeds up your heart. The way caffeine works is it keeps the C-amp active. So in a normal situation, norepinephrine binds the beta receptor, you get C-amp, C-amp opens the calcium gate, and extra calcium comes in. And then that's it, you're done until the next time norepinephrine binds. Well, if you have caffeine in here, the caffeine tells the C-amp, hey, keep opening calcium gates, don't stop. So if you have caffeine, norepinephrine binds the beta receptor, you activate the C-amp, and then caffeine makes it stay active. So then it keeps letting extra calcium in. We also have nicotine and cocaine. You may have heard that when people overdose on cocaine, they die of a heart attack because cocaine also makes your heart race. These two both have the effect of increasing your norepinephrine. So they either stimulate your neurons to secrete more norepinephrine, or they're blocking the reuptake of norepinephrine. And if you remember back to chapter 12, we talked about how cocaine blocks the reuptake of norepinephrine. So nicotine, you will secrete more, and cocaine blocks reuptake. So the point is you have more norepinephrine. So that higher level of norepinephrine is going to bind more beta receptors. Okay. Then if we go back and look a little more at negative chronotropic agents, there are things that will slow down your heart besides acetylcholine. But the other negative chronotropic agents act by blocking the effects of norepinephrine. So we do have negative chronotropic that slow the heart rate simply by blocking norepinephrine. Norepinephrine speeds your heart up. If you can stop the norepinephrine from doing that, your heart won't speed up. And if it's not speeding up, then it's slower. It's basically like taking away the gas pedal from your car. You can't speed up your car if you don't have a gas pedal. And you always have some level of norepinephrine in your body. So if you can block norepinephrine from acting on your heart, then your heart will slow down. This would be the beta blocker drugs and the calcium channel blocker drugs. So these are medications that people take usually to treat high blood pressure. The beta blocker drugs are going to come in and they're going to prevent the norepinephrine from binding to the beta receptor. Then none of this stuff happens. No C-amp, no calcium gates getting open, no extra calcium coming in. The calcium channel blocker drugs act over here. You can still have norepinephrine bind, you can still have C-amp, but they're going to come here and block this so that calcium can't get in. So beta blockers are going to work because they prevent the norepinephrine from binding. So you can still have norepinephrine floating around in your body, but now it can't bind to the receptors. And the calcium channel blocker drugs prevent the calcium from coming in. Then another negative chronotropic agent we have is electrolyte imbalance. And especially potassium. And we're going to learn more about this in chapter 25, but keeping your potassium level at homeostasis is very important, because if your potassium level is off, it can mess up your heartbeat. It can actually even cause your heart to stop beating. So this we'll talk about more in chapter 25 with the electrolytes. Okay, so those are chronotropic agents. This is how you alter your heart rate. Let's keep looking at other factors that would affect cardiac output. So we have venous return and Frank-Starling law of the heart. You have about 5 liters of blood in your body. Remember that from chapter 18. You have 5 liters of blood. When you are resting, you don't actually need all 5 liters. So you use your leg veins as a reservoir to hold blood while you're resting. And that's what this is showing. This is when you're at rest. 64% of your blood is hanging out in the veins, and this is mostly in your legs. So you kind of store that blood in your leg veins. And we'll talk more about this also in chapter 20 when we learn about veins, but that's why you get varicose veins in your legs, because that's where you store blood. And the blood doesn't actually stop flowing. It's just that the veins in your legs when you're at rest will widen so that more blood can be in them, and that blood flows through very slowly. Okay, then when you become active, you do need that blood. So now you've got to get all this blood in these wide veins that's flowing slowly. You got to get it going again. So what you're going to do when you go from resting to active is your muscles squeeze those veins. So you can see here's relaxed, and see how the vein is wide and the muscles aren't pushing on it. Then when you become active, the muscles squeeze that vein. They make the vein narrow. So again, kind of think of a tube of toothpaste. You've got all this blood in your leg veins. When you become active, your muscles squeeze those veins in your legs, and that forces that blood back up to the heart. Now you're putting more blood in the heart. This is increased venous return. So you're going to have more blood entering your right atrium. Remember end diastolic volume? The amount of blood that fills the heart? That number is going to go up now. You're now going to have a higher end diastolic volume. You're filling the blood with more, you're filling the heart with more blood. So now two things happen that you're filling the heart with more blood. On the one hand, stroke volume will increase simply because if you put more blood in there, there's more blood to pump out. Very simple, very straightforward. Don't overthink that part. More blood in gives you more blood to pump out. The other thing that happens is the Frank-Starling law. When you put more blood in the heart, that stretches the heart. So more blood in the heart stretches it. Think of like blowing up a balloon. The more air you put in the balloon, the more you stretch the balloon out. Okay, think of the heart like a rubber band. If you're shooting a rubber band at someone, the more you stretch the rubber band, the harder it's going to spring back. It's like that with your heart. Your heart, like a rubber band, the more you stretch it, the harder it springs back. So by having more blood in there, stretching the heart more, you cause it to increase the force. And if you increase the force, you increase the stroke volume. And that's the Frank-Starling law. It just says that if you put more blood in the heart, you will stretch the heart, which will cause it to contract with more force, which will increase your stroke volume. So increased venous return increases cardiac output by increasing stroke volume. So the increased stroke volume leads to increased cardiac output. And you have the two different ways you're increasing the stroke volume, simply by having more blood in there and by getting the Frank-Starling law where you increase the force of contraction. Now we'll look at inotropic agents. Inotropic agents are outside factors that are going to alter stroke volume. So let's review that heart muscle cell. We know that if this is the muscle cell, we know that we have beta receptors where norepinephrine can bind. It activates C-amp. Remember, this is what the muscle and the node have in common. The C-amp opens calcium gates, extra calcium comes in. But now here's the part where we differ from the nodal cell. That extra calcium gives you more cross bridges. Remember, more calcium's coming in to bind to troponin to move tropomyosin and get more cross bridges. And more cross bridges means more force, and more force means more stroke volume. So let's see what factors can act on this system. So if you remember parasympathetic, Remember when we first drew that picture, we had the picture of the nerves going to the heart? The vagus goes to the nodes only. Remember, the vagus does not branch down to the ventricles. So there is no acetylcholine to the muscle cells. So parasympathetic has no effect on force. So parasympathetic does not alter your stroke volume. So remember, we're not going to have any parasympathetic with the stroke volume. Parasympathetic can reduce heart rate. It cannot reduce force. Remember that sympathetic does increase force. Because the norepinephrine combined, you get the CAMP, you get the extra calcium. This is what sympathetic does. So this is the cycle of what norepinephrine does. So sympathetic will make your heart pound. So when it comes to inotropic agents, sympathetic is a positive inotropic agent. So we're going to have sympathetic, the norepinephrine. Because of this whole cycle, it binds to the beta receptor, activates CAMP, lets calcium in, and you get more cross bridges. Okay, another positive inotropic agent is one you already know, the digoxin. Because remember, it traps the calcium inside. The calcium can't get back out. So under normal circumstances, the calcium comes in and then it goes back out. So with each heartbeat, that calcium is constantly moving in and out. But if you have digoxin here, the digoxin blocks the exit. It traps the calcium inside. Remember, it's the Hotel California. So then you get a buildup of calcium. And then this buildup of calcium allows you to have more cross bridges. Okay, then when it comes to negative inotropic agents, remember, we're not going to put parasympathetic here. That's why I did not write this in green. Negative inotropic agents are going to work by blocking the effects of sympathetic. So again, beta blockers and calcium channel blockers. If you want to make the heart have less force, the only thing you can do is take away the gas pedal. Take away the sympathetic stimulation that's making it have more force. So that's how negative inotropic agents work. And also, electrolyte imbalances can be a negative inotropic agent. One more thing we're going to look at here that affects cardiac output is afterload. So remember, your ventricles pump into arteries. And think about taking your pulse. You can feel your pulse. Your pulse is that blood being pumped into your arteries. So arteries have to stretch. You can feel your pulse because you can feel your arteries stretching. So every time a ventricle pumps into an artery, the artery has to stretch to receive the blood. Okay, sometimes people can get artery disease. Like you can have atherosclerosis, you can have plaque buildup, so you can have problems in your arteries that prevent them from receiving the blood. If you look here in this picture, they're showing a little clamp on the artery there. So the heart's trying to pump blood into the artery, but the artery is not receiving it. So the artery could be clogged up, or it can be hardened. You may have heard of like people having hardened arteries. If that's the case, the artery won't receive all of the blood that the ventricle is trying to put in there. So your heart is working really hard and it's trying to maintain this cardiac output and pump the blood in there, but the arteries won't receive it. And that is called afterload, because what this ends up doing is it increases your end systolic volume. There's more blood left in the ventricle after your heart beats because the artery refused to receive that blood. And that higher end systolic volume is the afterload. It's what the arteries refuse to receive.